Welcome folks, in today's lesson we're going to talk about things that sparkle, things that glisten, things that twinkle. And as you look up into the night sky, you may see lots of this glistening, and you may ask yourself, what is a star? How hot is a star? And do all those stars look the same up close? And maybe you might look a little bit closer to home and say, what type of star is our star? So in today's lesson we're just going to talk about star characteristics. Now, when you are able to get a little bit closer to stars to view them like scientists would using a telescope, they would start to see some clusters of stars, and they would start to see some star patterns. And maybe they would see, different colors of stars. They would see stars that differ greatly in terms of size or luminosity. And this is a star cluster full of younger stars that don't shine as bright, and that way they're able to see all the individual characteristics that make up the stars. So let's look at some of the different ways that stars differ. So the question might be, how do stars differ? Well, they can differ in many different ways. They can differ in terms of mass, in terms of color temperature, and in terms of luminosity. And we're going to explore each one in a little bit more detail right now. So if we talk about mass, okay, the sun, maybe you can have a quick thought as to how big you think the sun is. How big do you think that sun is? Well, if you said that the sun was 2.0 by 10 to the 30, that's 30 zeros in kilograms, then you'd be absolutely right. Now, the question is, another question might be, how do we even know the sun is that heavy? I mean, clearly we can't put it on a mass balance or anything. And that's maybe something for you to research or find out yourself, doing a bit of independent learning. But if we look at this graph, just to have a look at where our sun fits into this, when we're looking at the graph, the mass of the sun is fixed as 1, so everything is relative to that. So our sun is somewhere in this group here. And there would be, the relative number of stars would be 50 stars. Now this is out of 261. So what we're seeing here is that there's a good cluster of stars that have the same mass as our own star, the sun that is, and about quadruple that rather, have a lower mass. But sometimes we think that our sun is so big, and there are reasons why, of course, because it's so slow to us. So close to us rather, but about 10, relatively speaking, 10 of those stars would have more than double the mass of the sun. And then, relatively speaking, there's a few stars that have an enormously bigger mass, 100, 150 times bigger than the mass of our own sun. So you can see again, our solar mass would be somewhere in around here in this grouping. So that's the mass. We also said that we can define stars in terms of their color temperature. Now I've put those together because the color tells you something about the temperature. So the color of a star gives scientists a clue about its temperature. So I got this little visual, this little diagram looking at some of the stars just to give you an idea. And many students would get a little bit confused here because they would automatically think that red stars and red things are the hottest. But in actual fact, in physics, in nature, wavelengths and things which are red in the visible spectrum have less energy than things which are blue. So in actual fact, the temperature increases as you move up from bottom to top there. And we can see that the color gives you an idea of the surface temperature. So Antares is a red star, and that has a temperature range between 3,600 to 2,000. Whereas if we go up to Spiga and the Virgo cluster, blue stars have a temperature range from 28,000 to 11,000. So much hotter temperature. And the hottest ones are blue and white. So that's another way of categorizing. And the final way that we can talk about stars is we can talk about luminosity. Now, if we look at this little visual here, we have the star which is known as Betelgeuse, is the one that's shining bright. And Betelgeuse, or Betelgeuse, is a very, very luminous star. Scientists believe that it's almost ready to explode and do something interesting like a supernova. If you want to or find out more about star lives and how a star moves through its life, then we'll cover that in a different video. But clearly Betelgeuse is more luminous than some of the other stars around it. So the question is, how do we measure that, or how do scientists talk about that in terms of luminosity? Well, there's two different things which I have to make you familiar with at this point, and they are the concepts of apparent magnitude. And apparent magnitude is how bright a star appears. And distance, things like distance, is a big factor here, because how far you are from the star would compromise or would change how bright it appears. And so scientists, instead of using apparent magnitude, scientists and astronomers use also another measurement of luminosity magnitude, which is absolute magnitude. Now, absolute seeks to talk about how bright a star actually is, and there's mathematical ways that that can be found. So those are some of the ways that stars are characterized in terms of their characteristics. This brings us to a wonderful tool that scientists sometimes use to look at stars and find out where stars are in terms of their life, and find out a little bit more about the star. When they map the different stars and they map temperature against luminosity, you'll see that there's a portion where a lot of the stars seem to align, and there's a pattern running in what I've circled here. And this is sometimes called the main sequence. Now, the main sequence is important because the main sequence is what astronomers have called that time in their life, a star's life, where they're just chugging along, call it midlife, where they're chugging along, burning energy, not at the beginning, not at the end of their life. And they have realized that stars which are at the beginning and end of their lives are anomalies from that main sequence. So scientists can use something called the hertzsprung-russell diagram to look at stars at different points of their life. So this is a color version of the hertzsprung-russell diagram, and in this color version we can start highlighting some areas here. Again, we can see that there's the main sequence. Most stars would fall within that, and if scientists map the temperature and the relative luminosity, and they find that the stars are up in the top right corner, that is to say they've got a low temperature but a very high luminosity, then these are what are called supergiants and giants. They've got a very low temperature, so they're probably going to be red or yellow, but they have a high luminosity, which means that they're starting to get bigger and bigger and bigger, maybe before the star starts to burn out. And then a little bit after that, we have this group down here, which have a very high temperature reading, or relatively high temperature, but not much luminosity. And the reason for that is they're very small, but they may have had an explosion or a nebula, and so they're burning extremely hot, but not so bright because they're much smaller. And these are called what scientists call white dwarfs. So let's have a look at some of that categorization here. Scientists, I've just put a chart here. Scientists have started to categorize stars and started to put them into different groups, classifying them as you would with music, classical, hip-hop, jazz, techno, and so on. And the main sequence stars are over here, F and G. And scientists decided, you know what, we're going to catalog all these stars, and that way we can find out more about them, what they're burning, what they're made up of, what part of their life that they're in at the moment. And this star classification leads us to a very important scientist in terms of astronomy. And her name was Annie Jump Cannon. And Annie Jump Cannon was the first main scientist to start categorizing these and putting these stars into different categories, classifying, if you like. And Annie Jump Cannon was around when she had to overcome a lot of obstacles. She had a lot of physical obstacles she had to overcome, but also attitudinal and societal obstacles. And towards the end of her career, she began working with another phenomenal scientist called Cecilia Payne. Now, Cecilia Payne worked with Annie Jump Cannon and took this a step further. And she actually began a very important process of looking at what stars are made up of. So Cecilia Payne actually tried to look inside the star and found out that they were made up primarily of hydrogen and helium, which was very interesting at the time because most leading scientists of the day felt that the stars were made up of the same thing that the Earth was. So think about how amazing this is to be able to understand stars, to be able to categorize them, to be able to figure out what stars are actually made up of. Having never actually been to a star, and maybe in the future will never be to even close to a star or send a telescope to a star, we've managed to figure out all these things. But there's still a lot to figure out about stars, and hopefully you keep questioning, you keep looking up into that twinkling night sky, you keep asking questions. And if you found this video useful or helpful, please give me a thumbs up and please consider subscribing to my channel.